Hello, my name is Anton Hristozov, and I'm presenting a paper based on sensor data protection. I come from Purdue Polytechnic, which is in Indiana, but I actually work in Pittsburgh, Pennsylvania, and originally from Bulgaria, so for me this is a special occasion to come all the way from the United States. Do I have a tweeter?
There's no.
There's no tweeter? Okay. All right. So I have three more co-authors that you can see in the actual paper that are not here. One of them was supposed to come, but he couldn't, so I'm presenting to everybody. So these are the main points that I'm going to go to. I'm going to talk about sensor and actuator attacks, and then I'm going to talk about enforcers and then data guards, which are the main things that are discussed in the paper. Then I'll talk about UAVs and usage of those data guards. Okay, thank you. And then I'm going to talk a little bit about the autopilot PX4. You know, there are PX4 and autopilot and a bunch of other different autopilot that exist that are open source. And then I'll discuss a case study with how this was implemented to a GPS attack. And I'll finish with some future work. Okay, so talking about the sensor data, starting with that, I just want to talk a little bit about what robotic vehicles are and why they're important. They're cyber-physical systems because they have physical part, they have a cyber part, but at the same time they're moving. And that makes it very challenging because when they move, they change their environment, things happen to them. They rely heavily on sensors and actuators, and also our real-time devices. And all these things make sensor work very important. Now, the sensors can have failures, and at the same time, there could be sensor attacks. Those two can bring problems to the controllers that use the sensor data, and then you could have issues. Now, the sensors are more vulnerable compared to the actuators. And the reason is, first, the sensors are many. There maybe, if you look at the autonomous vehicle, there are tens or hundreds of sensors that exist. Therefore, too many places to attack. And the actuators are fewer. Maybe if you have four wheels, then you have four motors or two motors or whatever, but there are limited number of actuators. The same is true for a quadcopter. It has only four motors and they work independently. But nevertheless, it's still possible through EMI, which is the electromagnetic interference, to generate enough strong signal to be able to affect this actuator, which means to change the speed of the motors. So all these things are explored, and you could find in my paper, you could see the references to papers that discuss very much in detail how this is done. And now, how can we do this to detect? It's very hard, especially if we have stealthy attacks. I don't know if you're familiar with that, but the stealthy attacks, like simply put it, are attacks that are changing the data very slightly over the course of a long time. For example, if I have a vehicle just flying over a certain country, like for example a big drone, and if I can start sending fake GPS coordinates that are slightly off every single iteration, then I could veer it off and land it in another country possibly, eventually after several hours, without the vehicle detecting it. And this is called stealthy attack. This is just an example. They're difficult to detect, and that's why I'm looking at a case study that explores this, how to do it. Okay, so just going back to the basics, and I know that one of you presented the Simplex Architecture the other day, so I remember that. So here's another iteration of that. I'm just going back to that just so that I can build up the case for data guards. And the secure controller that you see in green here, is this one? Oh, yeah, here it is. The secure controller is the one that is kind of second controller that it's much simpler than the main controller, which is here, the complex controller. And the secure controller can take over only if there is a problem detected, and then the switching component can switch to the secure controller. Maybe we can say the drone will just hover, but it will not fall from the sky and basically crash. So if there is an attack, or if there is a problem with the work of the complex controller, then we could use this secure controller to take over and eliminate the work for this temporarily until we stabilize. So this is how the Simplex architecture works. So building on that, there is this slew of papers that are working on the concept of enforcers. So the enforcers are similarly small things that exist, like small pieces of code, you could call them components, like software components, that can follow what's happening in the entire system, read the sensors, like here, the two sensors, and also read the reference, which means where we're going, and control the multiplexer. If they find that this controller somehow is outside of the limits, they'll intervene. And that's how the enforcer works. What is good in this approach is that an enforcer, let's say, is maybe 1,000 lines, and this controller is maybe 100,000 lines. So that's the difference between the code and the complexity. Therefore, we can trust this one, we can use some verification tools to prove that this code is indeed trustworthy, as opposed to some big code that runs in some operating system. And then we can say that there is a portion of the system that is completely trustworthy. And we can have many of those. We could have one that controls one parameter, we have a second one that controls a different parameter, and so forth. Now, this is how we can come from enforcers that are enforcing behavior to data guards. The data guards are basically small pieces of code that are like components, software components, dedicated, that are working on the premise that they want to enforce data contracts. So the data contracts are, all these things are introduced in the paper, data guards and data contracts. But they're basically working on assumptions and guarantees like all software contracts. This set of A is the set of assumptions and G is the set of guarantees. And they're making sure that we want to just go and make sure that all these guarantees will be guaranteed every time we receive the data. So this is similar to when you have, in machine learning, you have all the data, a set, and then you're running this set, and you're looking for outliers and things that you want to filter out of the data. This is kind of similar, but this is happening in runtime, and it's just smaller scale as far as complexity goes. So for example, if I wanted to create simple rules here, we could see this set of guarantees, G1 to G5. I just want to say every reading, DI, is smaller than the absolute maximum reading that I want to have for this sensor, or bigger than the absolute minimum reading that I want to have for this sensor that makes sense for this physical value. Similarly, I want to make sure that two successive readings will never exceed a delta. If that happens, maybe I'm attacked. Maybe something happened to my sensor. It broke or something else. Similarly, I don't want my sensor to be stale. I don't want successive readings to be, they have to be not equal to zero for a certain period of time. Let's say for 10 successive readings, I would like to know that my sensor moves. Maybe it's a little noise, but still I don't want it to be flat, because if it's flat, maybe it's dead. So this is another rule that these are all rules that you could create and come up with your data guard assumptions and guarantees. And this is similar if I find out that a particular reading belongs to the unacceptable readings, to the set of unacceptable readings, then I'm going to say, I'm going to replace it with the default value that I trust more than something that is completely an outlier. So this is just the introduction to what the data guard does. Yeah, so I wanted to just go over a control diagram for UAV, just a very high level refreshment of how things are done in UAV. And then we will exploit where data guards can just go and help with the situation. So we have, normally what we have is we have a mission controller that could be on board or could be off board. This could be a separate computer or could be on the UAV or any type of vehicle, robotic vehicle. Then we have a position controller, attitude controller, a mixer that takes this value and makes it into 4 different values that go to the actuators, in the case of the quadcopter. Then we have the sensors. We have sensor fusion, which basically fuses all different sensors sources. And then we have the observer. So this is so if you have looked at the control theory book or took a control theory class, you have seen a version of this diagram somewhere or something like that. So this is more like what a typical autopilot kind of looks today. So this is just a refreshment. And then if we look at this in a simpler fashion, we could introduce the data guards after each sensor, before the sensor fusion, or even after the sensor fusion, we could have one. We can also introduce a data guard after the controller before it goes to the actuator. Because we want to make sure that whatever the controller came up with, because imagine the controller is doing matrix multiplication and things like that. So if I have something wrong here because maybe somebody came and changed the coefficients somewhere in the memory, some attacker, then I will end up with a value that will pretty much make that robotic vehicle go crazy and do something weird. But if I am able to detect that and also keep it in certain norms, then I have better chance of surviving that accident. Similarly with the sensors. With all these sensor attacks where people are using EMI or acoustic waves to control IMU sensors, we could change this value to be outside of the norms. And all this logic doesn't know about it. It will just go and execute it because it's just math equations, right, especially the controller. And what will happen is unpredictable. So that's why the data guards are really a way to improve reliability and to also increase immunity against attacks. Next one is what a simple data guard can do. So we have all these rules that I looked at. These were the formulas that I had, like 5 guarantees. So now we have this in the diagram. Checking the range of the inputs, then checking the delta between 2 successive inputs. We have a timer that just checks this, and then there is a way to detect if there is stale data, if my sensor doesn't change over the course of the last several readings. And we have the default data somewhere in memory, and we have a timer that just makes sure that we don't go out of the limits of the stale data time. So we could have different rules and add blocks here and design this the way we want. Now, this is another slide, one of those that I want to describe quickly the PX4 architecture, and if you're familiar with it, excuse me, but just everybody so that we're on the same page. So the PX4 is an autopilot. It's one of it's the one that comes from Switzerland, from UPH Zurich. It's open source. You can just go and look at the code, change it, build your own drone and put it there and make it work. So the architecture is interesting in many respects, and written in C++, C and C++ mostly. And it has this thing in the middle that's called Object Request Broker, which is implementing the publish-subscribe model, where we have all these modules, like these flight controllers, state estimation, all these different software components, where everybody's sending messages to each other, and other modules are subscribing to the messages. And then we have all these many-to-many relationships to messages, but completely independent components. And then we have the operating system here, the drivers, and the... Okay, so this is before. So the experiment that I did, that in order to kind of work on this and see how it could be implemented, and I had a mock-up implementation for PX4, was to simulate a stealthy GPS attack. This is similar to the type that I described, where slightly modified GPS readings are sent to the drone, and the drone is veered over the course of certain hours or minutes into a different direction. So for this, I used Gazebo, which is a simulator that works with PX4. And this is the PX4 autopilot. And you could see the drone flying. I also used another tool that is not shown here that describes the actual trajectory. It's like a mission application. But in the PX4, what could be done is to add another message to basically change the GPS message to be called something else, like a raw GPS message. And then it goes directly to the data guard. The data guard checks it for sanity and improves it if it needs to be. And then at the end, it sends the original GPS message, which is now without the issues that the raw GPS message might have. And that's how the rest of the system doesn't realize that has happened, because it's done via indirection. It's basically a caught here by the dart and modified if necessary and sent back here. And that's how this experiment was done to get some understanding how easy or difficult it is to be done in a real autopilot like PX4. Right, so the future direction that I want to talk about a little bit are related to what can be done in this respect. For example, the simple implementation that I have is just very trivial. It's just looking at how quickly the GPS reading changed from reading to reading. It looks at outliers. It looks at lack of change, for example, for certain periods of time, all these things that I discussed. But this is relatively simple. So we could say, if we have a more complex sensor, what can we do? Well, we can do anything. We can even use machine learning and look at the trends of data, let's say, of this particular sensor. And all of a sudden, if something changes that shouldn't, then we know that something has changed in our environment. Maybe somebody attacked us or something else happened. And when I say AI here, I don't mean like full-fledged AI that requires GPUs and like we were in the previous talk. It may not be that. It could be even a simple algorithm that very efficiently was developed in C and implemented as a component that very well works in an embedded environment. So the field of machine learning, it doesn't have to be in Python, doesn't have to be in using like PyTorch or TensorFlow or something like that. It could be anything that makes sense for that particular situation. Even if it's not called machine learning, if it's called anything, any algorithm that you think is appropriate, that is more intricate than the one that I showed. So another direction, and by the way, each of those bullets could be another paper, right? If somebody is interested in that. But I'm just listing what comes to my mind that could be a future work for this. Another way to look at this is if you look at data description languages, like data flow languages are a little bit higher level languages that could describe data. So if one could describe a data guard to a higher level language and then has a tool to say, generate my data guard code in C, for example, or Python, that could be another way to just look at the problem and automate it. so that it's applicable to different types of sensors. The reason for that is because the number of sensors is growing. We see the autonomous cars are having many of them. It's like the CPUs pretty much. Many CPUs, many sensors, many problems because it's inevitable. In many ways to be attacked, many ways to be, the MAX 737 was also mentioned the other day, and that the failure of that airplane was because the sensor failed. And the situation when the sensor failed was never simulated. And it happened in the air with 300 people on board. It happened 2 times in the course of 6 months. So that's why the importance of sensors and their failures, depending on whether it's natural failures or failures that happen because somebody maliciously introduced something, the effect is the same. We still have a problem with reliability, and with safety critical system, we have a critical problem, which means there could be loss of life and loss of equipment and things like that. Similarly, there's another trend that I can see, adaptive data guards, where sensor data may change if we put the sensor in different environments, and therefore we might need to adapt the data guard to reflect the change of data generation. And finally, I'm thinking that maybe someday the manufacturers of smart sensors may integrate some of these features in the sensor so that you just have all these kind of first level protection inside the sensor, as opposed to transporting this through some buses coming to us in the controller, and for us to be able to intervene maybe a little bit later. So these are all the things that I just wanted to present to you. And I think that's it.
Thank you very much.
Thank you.
And I will open the time for questions, please. Yes?
Yes, so I mentioned that your presentation was really interesting. And I would like to ask whether you're planning to test your solution on real hardware, EBS. How would you like to simulate the environment, provide some noise with the GPS?
Yeah, so for example, in this case, I'm going to go back. Yeah, so in this case, in the gazebo simulator, I'll start with that and then I'll answer your question. But in this case, the gazebo simulator has plugins. So there's a sensor plugin. So I went into the sensor plugin and I introduced the random noise in the GPS. So similarly, if I have a real drone or a real vehicle that requires some type of localization, like GPS or non-GPS, if we're in a room like that, it could be some optical localization. So you have to basically go into that system and to introduce some disturbance into the generation of, for example, if it's OptiTrack, I'm familiar with the OptiTrack system, which is an optical one. You could go and manipulate the packets that it sends so that you can sense occasionally, maybe you send something else. And then when you catch it, and this is what I did with this was just easier for me to do because I could do it on my laptop. But it's a good point that it could be used for a real system in a similar fashion, but you have to work with the generation similar to the GPS attacks. The GPS attacks are basically, they're called GPS spoofing attack because they're sending GPS signals that are sent by somebody else, but because when we receive, we don't know if it's somebody else. We think it comes from the satellite. So this is kind of a similar thing with this. We could generate something that, depending on the method of localization.
Thank you. Some other questions, please? Yes?
Don't mind, but anyway,
It's okay.
they're data, and I'm back at some of this. So for me, it's interesting because you are extracting the data rules from the data, and you got probably the server specific, so you're exactly on which server. And that is really saying to me, you're taking because you're talking about this adaptive models for the future. But then this means that interface changing very distribution. this data graph rules the
Right.
how would you use, right? Or
No, I think I know the answer to this question. So at least one answer. It may not be the one you're looking for, but I think there are two types of methods to do things in the control world. In this control world, there's two ways. One is the model-based approach, which is this. So you have a model in this controller and in this controller, and this works exactly by the model that's described by the equations. The other way to do things is to do data-based approach. So all the machine learning and all these things that we do now are data-based approaches. So what I'm saying is that now we're doing all these things with the model-based approaches, but we have to introduce data-based approaches. So the data-based approaches are nice, as you said, when data is known.
we can get private approach.
Excuse me?
We can get private approach.
Right.
I mean,
That's what I'm saying. Of course. I agree. But what I'm saying is this is the classical approach. And we both know people that are living in that world. And then we have the data-based approach, which is the other world. And there's the hybrid approach. But the thing with the data approach only is the issue with how do you behave when the data changes. And maybe the hybrid approach is the solution for something that's more deep, that really can be, and that you heard in the previous talk when the presenter was talking about adaptation, how systems and agents should learn as they go into different environments. So this is it's all connected, right? This is how can we learn if we don't have a model? It's kind of hard if we just rely on data. So what I presented is mostly data-based, purely approach because it's a simplistic way. I know this sensor, I know how it behaves, and I know how to basically protect it. But if something changes, then I have to come with something more complicated, and I don't have the full answer for it today.
It will be the same with being a learning. So I mean, I think it's learning from the sensors. Because it's quite
Yes.
reliable. But this was the mind that it's possible use data graph rules to be continued that data will get invented by the day change in the definition.
Yeah, and I was mentioning that you could put something more complex in the data graph that basically accumulates statistics as it goes and maybe forms certain rules about the data as it goes. And then if I have, let's say, the last 2 weeks in certain conditions and my conditions haven't changed, but my data has changed, then I can understand that something has happened. And then in different set of conditions, then I can form different rules. So it's possible. I still don't know how to exactly implement it, but I understand what you're saying. Yeah. So I don't have a better answer for you, honestly.
Your question is my
Yes, probably. I don't know.
My question also, what's the rate of the things that you need to catch up in real time at the level of sensors?
Yes.
And what can be done in background in already stored data in some data files or database? So it's always a balance. So,
and it's sensor specific because some of those sensors are like 1 kilohertz, like 1,000 times a second, right? And some of them are 400 times a second reading. Some of them are less. And some of the sensors are just giving you little data, but some are giving you a little bit more data. Yeah. So it's really engineering. You have to make the right solution for the right problem. I'm just presenting the idea of how this could be done, but again, I mean, because there's so many sensors and some of them are like vision sensors that are complex. Some of them may be audio sensors and something else. So I'm just presenting very simple because for the GPS, it's latitude, altitude, longitude. There are like 3 main parameters and the other ones are just timestamps and other things. So this is kind of easier to analyze and to start with.